called the Tuesday lab, next Tuesday that is. Next Tuesday would be the 20th, right? There is no lab on that day, but I will have this is announced also in Piazza, so make sure that you're paying attention to those weekly retrospectives we give. On Monday, of course, I will hold regular office hours. I will also hold regular lecture. Just understand that it'll also be posted online as well. So if you do need to skip that lecture, understandable. Make sure that you go ahead and watch the video of those so that you get the full notes. So today we're going to continue on searching and sorting. Normally what I do is after we cover searching algorithms, I move on to sorting algorithms. I'm going to switch the order a little bit instead today because you need some stuff for tomorrow's lab and of course for Thursday's hack. So what I'm going to do is I'm going to jump ahead to searching and sorting in practice in C, and then we'll hold off the discussion of the actual algorithms for Thursday and Monday. So just to review here really quick. Remember that we developed the linear search algorithm that took an array, its size, and a key element, and then it returned the index at which it found it. So it found it at the first, whichever one it found first that matched that, it returned that value. Alternatively, we could have done it with pointers instead, returning a pointer to that value. But what we discussed last week was, what if you want to do a linear search for doubles instead? Well, it's pretty much exactly the same algorithm here. It's a for loop, a comparison, and then a return statement. What if we wanted to do it for strings? The only thing that would change here is how we're comparing things. And if we're comparing a string to a string, we would use a built-in tool called Strcmp, right? String comparison, that looks at two strings A and B, and remember the contract there, remember the behavior. If A comes before B lexicographically, right, apples come before bananas, then it would return something negative. If a zoo comes before apple, right, or zoo comes after apple, but if zoo is over here and apple's over here, they're out of order, and so it returns something positive. If they're equal, it returns 0. Right? And we're going to use that contract today to develop a much better alternative than writing and rewriting the same algorithm over and over again. Right? If I wanted to do linear search for doubles, I would have to do cut, paste, change a few lines. If I wanted to do it for strings, cut, paste, change one line. If I wanted to do it for students and you wanted to search by NUID, I would have to do cut, paste, and change one line. Right? You don't want to do this. You don't want to repeat yourself. You don't want to do that copy pasta kind of design. So, how do we do it in practice? Well, in practice, you don't generally roll your own searching and sorting algorithms, right? Unless you have a very good reason to do so, right? And 9 times out of 10, you do not have that reason, right? 99 times out of 100, you don't have that reason. You don't roll your own, meaning that you don't write your own searching and sorting algorithms. You don't write your own linear search like we did. Instead, you use what's built in, right? In practice, you use built-in search and sort algorithms and functions in a standard library, right? You don't rely on you don't roll your own for every single one, because then you would get into the copy pasta routine. Now I need one for strings. Now I need one for students, right? You'd be doing that over and over and over again, right? To avoid multiple solutions, you use what are called generic searching and sorting functions. Right? There is a problem here. Let's focus on sorting first of all. The sorting algorithm, or a sorting algorithm or function, may know how to sort, but if it is generic, it may not know how to order. And there is a subtle difference here between sorting and ordering. Ordering is given two elements, A and B. Do they go like this? Do they go like this? Or are they equal? In other words, are they in order? Are they out of order? Or are they equal? So it doesn't matter. They're in order again, right? A sorting algorithm needs to know this because It's looking at two items. It knows how to sort. It's, oh, this one comes before this one. They're in order. Leave them alone. Or this one comes after this one. They're out of order. So what do I need to do? I need to swap them. Or a searching algorithm needs to know, does this thing match this thing? Does this thing match this thing? Does this thing match this thing? It's comparing a key to each element in the array. And it needs a criteria by which it says, oh, yes, that's equal, according to the criteria you gave me. But it's completely ignorant of what it's sorting. It just looks at these things as things. It doesn't say that this is an integer and this is an integer, so I can use the less than or equal to signs, right? Or this thing is a string and this thing is a string, so I can go ahead and use strcmp. Instead, what you have is and I'll draw a picture here instead. This is actually from the book. Here's the picture. The sorting algorithm is generic. It just simply takes an array. It doesn't know what that array is. It doesn't know that it's an array of integers. It doesn't know that it's an array of doubles. It doesn't know that it's an array of students or strings or whatever. Instead, and it knows how to sort things. It knows how to go through and put everything into a correct order. But it doesn't know how to compare things. It doesn't know how to order them. So what it does is it uses another piece of the puzzle here called a comparator. Given A and B, it needs to know, are they in order or out of order? Do I need to swap them or leave them alone? And so it hands these two things off, A and B, to the comparator. And the comparator is responsible for comparing them and saying, oh, A comes before B, or B comes before A, or they're equal. That should look familiar there, right? That ordering, that's exactly what strcmp does. If the first string comes before, lexicographically comes before the second string, it returns something negative. Otherwise, if they're out of order, it returns something positive. Otherwise, if they're equal, it returns 0. Once you've got this piece of the puzzle here, you plug in the array, you plug in the comparator, and now the sorting algorithm doesn't need to know how to order things. All it has to do is know how to sort things. Okay, are they in order or out of order? Out of order, okay, I'll swap them. Are they in order or out of order? In order, okay, I'll leave them alone. And it makes all those questions to the comparator. All you need to provide is the array to be sorted and the comparator that knows how, given two elements, how to order them. And then this generic sorting algorithm can take care of everything for you. Now you don't have to rewrite the same solution over and over and over again. What you do need to write over and over again is the comparator. You just need to specify how they're ordered. This thing comes before this thing, or they go the other way, or it's 0. Okay? So that's what we're going to focus on today. You can use a generic or a comparator function that specifies how to order two elements, say A and B. Right? And the basic contract is that given two elements A and B, which goes first? A goes first. Are they in order? Are they out of order? Should they be swapped? And a comparator function, again, takes these two elements and it returns something positive, negative, or 0 depending on the relative ordering of these things. Remember that it returns something negative. You can't read too much into that. strcmp, I think, just is guaranteed to return something negative, not necessarily -1, not necessarily -10. It can be, all you can read into, you might not be able to read anything into the magnitude of that number, just the sign. Is it positive, negative, or 0? And so that's the contract that we're going to develop now. All right? So let's focus on writing comparator functions in C. All right? Okay. So what? First of all, in C, comparator functions. Let me go ahead and get rid of this. There we go. A comparator function has the following signature. I'm just going to cut and paste this to show you here. And let me go ahead and go to the next line. Can I do that? There we go. Int CMP, the name is going to be different for each comparator that you make. And what it takes two inputs, A and B. What are those inputs, though? Const void star A and const void star B. Is it an integer? Nope. Is it a double? Nope. What does the const mean? Just as a review here, const means that you are not going to make any changes to it. We don't want to make changes to it because we're simply going to say, oh, it goes like this, or they're equal. So that's a guarantee that we're not going to change it. The star indicates that it's a pointer, but what kind of pointer is it? If this were a pointer to an integer, it would be const int star. If this were a pointer to a double, it would be const double star. But this one is a const void star, right? Const or void star is a generic void pointer, right? It can point to anything. Right? It can point to doubles, it can point to an integer, it can point to a string, it can point to a student. You've seen this before. In what context? malloc. What does malloc return? It returns a void star pointer. In other words, just a generic memory address at which it's allocated a chunk of memory for you. Here's your pointer pointing to the beginning of that memory address. What do you do with that pointer? You do a typecast. Int star. You put that in front of malloc. That forces the generic void pointer that's pointing to this chunk of memory here to suddenly become an integer pointer and treat everything in that memory location as an integer. We're going to do a similar pattern here. We'll start with integers, but that's the basic idea. It can point to anything. And if you've got a pointer that can point to anything, then you only need one type of pointer, const void star. Right? And it returns the comparator returns an integer according to the contract, I'll put that in quotes here, contract outlined above. That it's going to be negative, positive, or 0 depending on the relative ordering, right? So how do we write a comparator? And there is a basic standard pattern that you can follow. It's pretty easy. First of all, if I'm given two generic void pointers, it's just memory locations. I could compare their memory locations, but that doesn't really mean anything. Suppose that these generic void pointers are pointing to integers. I'm going to compare them by using the less than sign, the greater than sign, or the equals equals sign to see that it goes like this, or they're equal, right? But the problem is that they're still generic void pointers. So the first step in any comparator is to cast the pointers to a specific type of data, to the specific type of data you want to compare. So if you've got an expectation that those pointers should be pointing to integers because you are sorting an integer array, then you can cast them to become integer pointers. If they're pointing to an array of doubles, then you can cast them to become double pointers, right? Then you use the state of the object or structure to determine the proper ordering. If it's integers, then you simply just say, is this thing less than this thing? If so, return something negative. If they're strings, then you can go ahead and rely on strcmp to do the work for you. If they're structures, like a student structure, then I've got two pointers to two student structures. If I want to, say, do something more complicated, like, compare their last names. And Adams comes before Zorinsky, right? Well, that'll work. But what if they're both named Smith? Then to break that tie, Smith and Smith, you then go to, I don't know, Adam Smith comes before Balthazar Smith, right? A comes before B. So you could encapsulate that complicated comparison logic, and then maybe you've got two Balthazars, right? And then you could break ties by going to their NUID or something else unique. You can encapsulate all that complex comparison logic inside of your comparator function, right? But you would do that by looking at the state of the object. Then you return a valid integer value that expresses the order of the two elements. There we go. Okay. All right. We'll look at a couple of examples here, but I do want to have some best practices before we do that, so that we follow those best practices. Use descriptive. Of course, this is a best practice for everything. But use descriptive names for your functions. Right? Name it what you're comparing and how you're comparing them. Be explicit in your comparisons. Right? Avoid tricks. Like, for example, I'll show you later difference tricks. Where you take one common trick is to take the difference of two things, and you should. And it's a great trick the first time you see it. It's a terrible trick the first time that it fails on you, and I'll show you how. You can reuse comparator functionality whenever possible. All right. So what we're going to do is we're going to write several examples here. We'll write as many as we can because we do need to get to how to use them, actually. Come on. It's not being nice. Okay, now it's being nice. But it's not being consistent. There we go. There we go. So let's write a comparator first that orders integers in non-decreasing order. Now, non-decreasing, that sounds weird, but it's technically correct. Non-decreasing is basically the same thing as increasing, but what happens when you've got two 4s, right? Well, that's not increasing, strictly increasing, we say. So it's non-decreasing, right? Because at least it's not going down, right? They're equal. So think about increasing order, okay? Let me come over here and start writing this function. It's a comparator function, so it'll return an integer. What should I call it? I'll call it CMP for short, int. And we're going in ascending order, so I can put in ASC for ascending, or if you want to be more verbose about it. Or maybe that's just the default that you want to use. And usually ascending order, non-decreasing order is the default for many applications. So we'll go ahead and just give it a name of CMP int. Now, it's going to take two integers and compare them, so should it look like this? Int AB. Is that a comparator? Nope. A comparator has to have this signature. It's not just ints, it is generic. I have to make these generic. So is it an int pointer? Const int star A and const int star B. Now they're consts. I'm not going to be making changes to them. Now they're pointers, but it's still too specific. I need to make this as generic as possible for it to actually be a comparator. These need to be void pointers. Okay? Now, the understanding is that you're only going to use this comparator and give me integers. If you give me something else, that's on you, right? I'm advertising the fact that this is an integer comparator. Maybe in my documentation, certainly in the name, it says that this is a comparator for integers. If you gave me two doubles, I would treat them as integers, which is not going to lead to good behavior, right? It's not going to lead to the correct results. But then again, that's on you, right? You gave me an integer comparator and then gave me double elements to sort or something. Those are incompatible, okay? Again, we've got those three steps. First of all, I need to make these into integer pointers. So what I'm going to do is I'm going to create two const int star x and const int star y. And I'm going to cast const int star A, and I'm going to cast B, just like you do when you use malloc. Right? You don't use const because you actually probably want to make changes to it, but I'm not going to be making changes to it, so I want to keep my promise. I could get rid of this and break my promise. I don't want to do that, though. Right? In fact, let's just return 0 here for a second. Let's see what will happen here. All right, well, at least it gives a warning. I've disregarded the const. I have broken my promise. So now it's no longer it's strictly enforced. If I had done this in previous examples that I've showed you where you use const and then you try to violate it, it would have been a compiler error. But I'm doing it kind of circuitously. I am doing it through a typecast, so I'm kind of getting around that promise, but it still catches me, right? So, but it's allowing me to do it. So I'm not going to break my promise. I'm not going to make changes to what A and B point to. X and Y point to the same thing. I'm still not going to make changes through X and Y. And when I do that, it, of course, compiles just fine. All we're doing down here in the main tester is I've got an array of size 10. I print it. We're going to sort it eventually. And then we're going to print it again to see that it's sorted. Okay? So step 1, typecast so that you actually have X and Y here. Now you can actually use less than or equal to. If X is less than Y, then I'll return something negative. Right? Now, there are two issues here. First of all, can I do that comparison on line 7? X is less than Y. What are X and Y? They're pointers. They're not regular old integers, are they? So X is less than Y would be saying, is this memory address less than this memory address? Right? That doesn't make any sense because, it'll certainly answer yes or no, but it's not what you want. I don't care if it's stored in this part of my computer versus this part of my computer. Right? So what do I need to do to make those into regular old variables? Dereference X and Y. Now they're regular old variables. And I can compare the values actually pointed. X and Y is the value stored in X less than the value stored in Y. Return something negative, give me something negative. -2, okay. You want to be squirrely about it. I'll go ahead and keep it simple and go -1, right? Else if, now follow that pattern. If X is greater than Y, then what will I return? They're out of order, so return something positive. Give me something positive. 1, you can write +1 if you want to, but that's kind of ugly. Else, well, what's the only other case? They're equal, right? And so I would return 0, right? Now, here's the difference trick that I was alluding to before. What if instead I did X minus Y, right? And I return that value, return this, right? Let's think about what happens when they're equal. What happens when they're both 5? 5 minus 5 would give me 0. That works. What happens when X is 5 and Y is 10? Or let's go with 3 and 5, because I only have so many fingers here. They're in order, right? So I should return something negative. 3 minus 5 gives me, what kind of 2? -2. Something negative. Okay. Well, let's switch this around. What if it's 5 and 2? 5 minus 2 gives me 3, which is something positive, right? Why don't we just do that? Why do we have to write 8 lines of code when we could just return the difference between two things? What if one of them is very large, like 2.147 billion, and one of them is very large, negative 2.147 billion? Now what's their difference? So large number minus a large negative number would give me, say 2 billion plus 2 billion minus -2 billion would give me 4 billion. Is 4 billion representable by an int? Nope. Tricks are for kids. Don't do them, right? Don't do the difference trick. Avoid the difference trick, right? Don't do that, because it's very susceptible to overflow. Yeah? No, this Strcmp should be safe. Yeah. All right. What would this look like if I wanted to do it for doubles? Well, first of all, should I call it CMP int anymore? Nope. So CMP double. This doesn't change, because if this changed, it would no longer be a comparator. Right? What does change? Double. Copy. Double. Double. Oops. I'm not cutting and pasting the right thing here. Double, double, double. And guess what? Nothing else changes here. Right? But what if I did the difference trick here? Avoid the difference trick. Why? Up above, it's again, yes, tricks are for kids. This is susceptible. That's not right. Susceptible to overflow. What if I did the following? What about 0.5 minus 0.75? What is that equal to? -0.25, okay. So it's something negative, but what happens to 0.25? It truncates to 0. 0.5 and 0.75 are equal suddenly, right? So avoid the difference trick because of overflow, because of loss of precision, because of truncation, et cetera, et cetera. This is what I mean by it's best practice to be explicit. Go ahead and write 8 lines, because now you are being absolutely explicit that the ordering goes like this, and then when it goes like this, then we return something positive. Okay? Here's another one that I'll do. What if I wanted to do a comparator for integers, but I wanted to do it in reverse order? Right? So instead of I need to call it something else, right? I need to call it int. Instead of ascending, I'll call it descending or desc. Right? What should it look like? Cut, paste, and change a negative into a positive, and change a positive into a negative. That looks good to me. Or I could have switched around the less than and the greater than, but I copy pasted, right? What's a better solution? Okay, I've already got one, right? I've got CMP int here. I could call that, right? Int result is equal to CMP int A and B. What would I then return? The opposite being -1 times the result. Positive becomes negative, negative becomes positive. What happens to 0? 0 times -1 stays the same, right? Really cool trick there. And how could I make this even shorter? Don't store the result. How could I make this shorter still? Don't multiply. Instead, change them, right? If you compare A and B and it tells you that they're like this, this, or this, then if I swap them, then whatever the relative ordering was before will now be reversed. So I can reuse comparators here, right? And now all the heavy lifting is done by this one comparator, okay? We'll come back to, oh yeah, go ahead. Because if you don't, so why would we use generic const void pointers everywhere? Because then if you didn't, then you can't plug it into that picture there, right? This has to be generic. This has to be generic. Basically, the sorting algorithm has to be completely oblivious to whatever it's sorting, and so because there's going to be one sorting algorithm, which is what we're going to do now, right? There's one sorting algorithm to rule them all. There's only one sorting algorithm that you ever have to use, right? We'll come back and do some more examples, particularly with the student ones. But let's go ahead and now look at how you actually use these. And you'll see immediately what kind of use they are, right? So the C standard library, and that is stdlib, there is a function called qsort. And we will cover quicksort, which is its namesake, on Wednesday and possibly on Monday. But qsort is originally meant an implementation of quicksort. It's this very fast sorting algorithm. It doesn't necessarily mean that anymore. It could actually be a heap sort implementation. I think that's what BSD does. That is Max and stuff. And other, if you're doing your own C implementation, you're free to rewrite qsort into a completely different sorting algorithm. There's no guarantee that it's quicksort, but because they named it qsort 40 years ago, we're still stuck with the name. It takes 4 inputs, and I've separated them one to a line here. All right? The first argument is base. It's the array of elements to be sorted. Also note that it's not const. What does that tell you about that? It is going to be making changes to your array. It's going to be sorting it, right? Void star, it's also generic. Because we don't have a quicksort for an array of integers. We don't have a quicksort for an array of doubles. We have a quicksort, period, right? It can be used for any array of any type. And there's only one sorting algorithm that you ever need, qsort. The next one, nel, is number of elements. So nel is the number of elements in the array, right? That's pretty standard. Anytime you pass off an array to another function, you need to pass also the size, and that's where that comes in. Size t, don't worry about that. Treat it as an integer for all intents and purposes. Size is actually not the size of the array, is the number of bytes each element in the array takes. Why is that necessary? Because what the sorting algorithm is going to do is it's going to take this thing A and it's going to take this thing B and it's going to give it to your comparator and it's going to say, oh, they're in order. Okay, I don't need to do anything. Or it's going to say they're out of order. They need to be swapped. Well, it needs to take this thing and shove it over here and take this thing and move it over here. The only way that it can do that is by knowing how many bytes this thing is so that when I transfer it over here, I'm transferring the correct number of bytes. An integer would be 4 bytes and 4 bytes, so it's transferring 4 bytes between them. A double would be 8 bytes and 8 bytes, so it would need to transfer 8 bytes and 8 bytes back. A student structure, if you're sorting students, maybe that's 40 bytes, right? So it also needs to be told how many bytes each element takes. Usually, you use what? How many? What thing have we looked at before that tells you how many bytes an integer takes? Size of for this parameter. Okay. And finally, the last thing here is compare. What is that? It's a comparator. But all of that is new syntax there. I'm going to talk about it in a second, but what I want to do is show you a demonstration of how we use it. All right? It's actually a function pointer, right, which requires a little bit of deeper understanding. So let me go ahead and come over here and sort. So qsort, those 4 arguments, what am I going to be passing if I want to sort the array here? Well, the first one is going to be the array that you want assorted. The second argument was the number of elements in that array. So how many elements are there in here? Well, I already put that into a variable n. So I'll just pass in n. How many bytes does each one of these elements take? Well, it's an integer, so size of int. Right? And the last one is the comparator that you want to use. Let me go ahead and sort it in ascending order. In other words, I want it to use this comparator right here. All I need to do is pass in the name of the function. Let's go ahead and run this. Magic. The first one was unsorted. The second one is 1, 2, 3, 3, 4, 6, 8, 9, 12, 21. It's now sorted for you. What if I want to sort it not in ascending order, but in descending order? I pass in another comparator. Now it's 21 down to 1. Right? I didn't have to rewrite the quicksort algorithm. All I did, and I didn't change anything here except for, oops, I didn't mean to do that, except for the comparator that you plug into it. Again, this is that picture. This is the generic sorting algorithm. I'm plugging in an array, and I plug in the comparator, and a different comparator will lead to a different order and a different sorting, right? A different way of sorting it. All you need to do is write a now, instead of rewriting a sorting algorithm, instead of writing a search algorithm, all you need to do is pass in a new comparator. Right? Now, let's go back to this and understand the syntax right here. So compare is a function pointer to a comparator function that defines the order that you want to sort in. And since we've already covered the comparators, basically you write a new comparator, you have a brand new ordering. Right? So what is a function pointer? Right? That's what we'll understand for the rest of the, we'll cover for the rest of the day here. How can we pass a function to another function as an argument? Right? That's what we're doing up here in this picture, right? This is a function. This is a function. How do I say, oh, quicksort algorithm, quicksort function? Use that function over there to do your ordering. Normally, I pass in things by value, or in the case that I'm passing an array, I pass in something by reference. But all of that is usually data, right? I'm passing in an array of integers, or I'm passing in a single integer value, or something like that. Or I'm passing in a pointer to a single integer so that you can make changes to it. Generally, these are referred to as callbacks, right? And the reason that they're called callbacks is because here's the function. Here's my comparator function. I give it to this function over here so that it can call it back in order to get information. In other words, this back and forth right here, the sorting algorithm is calling your comparator back so that it gets additional information. You'll see this again when we look at GUIs, right? Here's another example with GUIs. You can define a button, but how do you specify the code that runs when someone presses the button? Right? You provide a callback. Right? When you create the button, you say, okay, create a button, make it shiny, make it red, make it have a text called execute. And also, when it gets clicked, go ahead and call that function over there. The way that you do that is by taking the function's pointer and giving it off to this creation function, this factory function that registers that callback. And again, the example that we're looking at right now is that qsort needs a way to order elements. So it needs a comparator function. There we go. In C, pointers can point to data stored in memory, right? I can have a pointer point to an array of integers. I can have a pointer point to an array of doubles. I can have a pointer point to a single thing, like maybe a single student or something like that. But a pointer is just a memory location, right? At the end of the day, it's just an address. So what else is stored in memory? What else is stored in memory? Think about when you start up your program, right? You start up the program, your program code loads. Then you call a function, you call a function, you call a function. We are creating stack frames. Where are those stack frames located? They're located in the computer's memory, right? So what else is stored in memory? Your code, right? So it makes sense that you can create a pointer that points to your code, or more accurately, points to a function in your code, right? Because it's just another memory location. The code for your comparator is sitting somewhere in memory. It starts at memory address X, right? Well, then I can have a pointer point to memory address X. And now my pointer is, instead of pointing to data, instead of pointing to an array of integers, now it's pointing to a function instead. And that's what we mean by function pointers, okay? Let me go ahead and go into code mode here. And let's just look at some examples, right? So let's create a pointer, a function pointer called ptr to func, right? That can point to any function that returns an integer, and takes 3 arguments. Right? Now we're going to get into the syntax here. An int, a double, and a char, okay? So that's what I'm going to do. I'm going to create an integer, I'm going to create a function pointer that can point to any function that returns an integer and takes 3 inputs, an int, a double, and a char, okay? To do that, I would use the following syntax, ptr to func, right? Int, double, char. There we go. And I'll set it equal to null because that's best practice. If you don't have, if you have uninitialized memory, then an uninitialized pointer, it can point to anything. I'll initialize it to null. Look at that syntax. The star tells you something, right? The star tells you that it's a pointer. What kind of pointer? The rest of the syntax tells you that it's a function pointer. I need those parentheses around the star and the name of the pointer. Otherwise, it would be treated as maybe as a dereference or something like that. The int this int right here specifies the return type, and then in integers specifies the parameter list along with their types. Right? Let's do another one. Let's do a simpler one. Let's go ahead and declare a pointer that can point to math's square root function. Right? There we go. So help me out here. How would I declare that pointer? First of all, let's call it ptr to sqrt. ptr to sqrt. Right? So what kind of syntax would I need here? First of all, remember sqrt, what does it take? It takes a single double, and it returns what? Also a double. So I would use double as the return type, a star in front of my function pointer name, and then it only takes a single input, double. And I'll go ahead and set it equal to null. Right? Now that's a function pointer. ptr to sqrt, it's just a pointer. It's not pointing to anything right now. It's pointing to null. But it can point to any function that takes a double and returns a double. Okay? So let's go ahead and make our new pointer point to math's sqrt function. How do I do that? Well, I can go ptr to sqrt is equal to sqrt. that should look familiar. If you were to call SQRT, how would you invoke SQRT? You would put parentheses, and then inside the parentheses, you would put the input, right? I didn't do that here. I just used the name. The name of a function is its pointer. It can be used as its memory address. And so I'm making this pointer here point to SQRT. Cool. You can also invoke the function via its pointer. So let me go ahead and call the SQRT function here. Double x is, or let's go ahead, double y is equal to ptr2 SQRT. Sorry. Move it over here. But now I'll go ahead and use parentheses, 2.0. What I'm doing is I am calling the square root function here. Give me the square root of 2, which would be 1.41 something something something. It would then return that value and store it in the value in the variable y. Right? Ooh, that gives me an idea. This is a whole world of hurt. SQRT is equal to sign. Uh-oh. What did I just do? Or what did I just try to do? Usually compilers won't let you do this. I made the square root function point to sign. What happens if you call the square root function now on, I don't know, 1? Will you get the square root of 1, which is 1? Nope, you'll get the sign of 1, which is 0, right? So, a whole world of hurt because you can make, thank you, I didn't know, I forgot what the sign of 0 is, right? Or sign of 1. Thank you, thank goodness it was different, because otherwise we'd be in a different situation here, right? I guess it's in radians anyway, right? So sine of pi or whatever. There we go, sine of pi would be 0. So I'm making square root point to a different function, or at least I'm trying to do that. Again, try to do this, the compiler will probably say, no, you can't do that. Let me go ahead and try here. Square root is equal to sign. And we need to include the math library to do that. Okay, yeah. L value required is a left operand, so you can't do this. But I could do something just as nefarious. I could make PTR to SQRT point to sign instead. And now when you try to invoke it, you would get completely different answers because you thought that this pointer was pointing to sign, but it's actually pointing to a different function that takes a double and returns a double. Right? So why would you ever want to do this? It's because you want function pointers. Let's go back up to our square root function up here. Right? Now that we see that syntax, now we can start parsing out what this means. This is a function pointer, because of this syntax right here, that returns an integer and takes 2 arguments, both of them const void stars, meaning that it takes a comparator function. And this is why comparator functions all have to have the same signature. Because if you had comparator functions with different signatures, you would need different versions of qsort that took a new kind of comparator each and every single time. And that defeats the whole purpose of doing this generic programming here. Right? This gets into object-oriented programming territory, generic programming and parameterization, and something called polymorphism. If you've ever taken a biology course, what's polymorphism in the world of biology? It's different phenotypes. So different cats have different coats or different stripes or something like that. In other words, within the same species, you've got polymorphic differences, but it's all the same species. The idea in programming is the same. You don't want to have to rewrite the sorting function for integers, rewrite it again for doubles, rewrite it again for strings. What you want to do is you want to define one sorting algorithm that works for all of the same species, all of the same types, right? All you have to do is change its stripes, change its how you're ordering things by plugging in a comparator. And the way that you do that is through a function pointer. You have to tell the function, use that function over there for comparisons, for ordering. And the way that you do that is by, what am I doing? I'm pointing. Right? You need to give it a pointer to a function that you want it to use. Okay? And that's the whole purpose here. Okay? Let's get some more practice in with our remaining time here. we're not going to have the definition of a student here, but let's go ahead and write some comparators for students. Remember, oh, here, type def, struct, and then student. Let's just go ahead and define it, right? We had int NUID, we had a char star first name, we had a char star last name. What else did we have? Double GPA. Oh, and then the date. Forget the date for now, right? You can go ahead and do that on your own if you want. But what I want to do is I want to complete our examples here. Write a comparator to order student structures by NUID, by GPA, and then by something a little bit more complex, last name, first name. And unfortunately, I'm not going to be able to test it because I don't have a bunch of student structures to just standing by here. But I do cover that in the prepared videos. Okay? So let's go ahead and take care of the first one, which was what? Structures by NUID. So int CMP student by NUID. Right? Label what it is, right? They call it what it is. I'm going to be comparing students by their NUID. And again, should I be passing in student A and student B? Is that a comparator? Nope. Not even passing in pointers to them is it a comparator. It has to follow this convention. It has to be const void stars on both of them. Yeah? It can be kind of, strcmp, for example, is not technically a comparator, but it has the same contract. So you can call it a comparator, but if you tried to plug it into qsort, it's not going to work. Right? You need something else. And we'll see that example with last name, first name when we do that. Right? So here's A and B. The first step is to typecast them as what you want, X and Y. Const student star X and Y, right, is equal to const student star A, typecasting A, and typecast B. Right. Now X and Y are students, right? Before, if I wanted to access the NUID, by the way, would I use dot operator or arrow operator here for X? It is a pointer, so what do I use? Arrow. Right? Before, if I did this, let's try it. A, get its NUID. Right? And int foo is equal to this. Right? Let me go ahead and get rid of this so it actually compiles. It's not going to understand what you're talking about. It's going to have a problem with A, arrow, NUID, because A, is that a student? Nope, it's a generic void pointer. Right? It's not going to interpret that as a structure that you can use the arrow operator on. So I need to typecast them. I need to make X and Y into actual student pointers so that I can go X is NUID, right, and versus Y's NUID. Right? What types are the NUIDs? Ints. Should I go ahead and start writing a bunch of if conditionals? If X's NUID comes before, in other words, is less than Y's NUID, then return -1, ... Do I already have something to do this for me? What? This guy right here. Right? So let me go ahead and move you down so it actually compiles. This is why we have, this is why we, let me move all the way down here because I know what's coming up. This is why we have prototypes so that I don't have to worry about the ordering. As long as you put everything into a header file, it does what's called hoisting. It takes care of, and it doesn't matter if you write this function uses this function. It doesn't matter which order you put them in. If you're using prototypes, the compiler takes care of all of that for you. I'm not using prototypes here, so I do have to be careful about the ordering. So I have something to take care of this for me, right? Return CMP int for your NUID. I didn't have to write anything, right? Or I didn't have to write those 8 lines of code. Excellent. What about GPA? What would that look like? CMP student by, instead of NUID, GPA. Right? Do the same typecast, but now I don't have, it's not integers and I'm not using the NUID, so what do I do instead? I have CMP double, right? return CMP double of x's GPA and y's GPA. But now think for a second here. How do you want to compare by GPA? If I were to sort a bunch of students by GPA, what would be the most natural way of sorting them? Would the 4 O's come before the 3 5's, or the 3 5's are at the top? 4 O's first, so is that ascending or descending? 4 O, 3 O, 2 O, hopefully never below that. Descending. Right? Is this descending? 0.5 comes before 0.75. Is that descending? That's ascending. So what could I do here? Well, I could rewrite that comparator, or I could write another comparator, CMP double ascending, or descending, sorry. You're right. Is this descending? I forget. No. Smaller comes before greater, because we return something, so they're in order, so it would be descending, and that's not what we want. It would be ascending, sorry. This is ascending, right? That's the default. We want descending. So what could I do? Oh, I could switch. Oh, that's another idea, right? I could switch them. Y's, GPA. Come on. Okay, there we go. Excellent. All right. So your great idea, just switch them around. Now I've got comparisons by GPA. Right? What about the last one here we'll do is, what about last name, first name? So let me go ahead and cut and paste that. Student by name. Right? So now let's think about the logic here. Let me move up. Okay, I've got students X and Y. I want to compare, Anderson comes before Zurinsky, right? So I'm going to look at their last name first. Right? How can I compare their last names? I've got X's last name, and I've got Y's last name. Those are strings. Use strcmp. Right? That's going to return something negative, positive, or 0, depending on the relative ordering of these two things. Now, if it returns something negative, that means we've got Anderson and Zurinsky. And we don't even have to look at their first names anymore, because we know that Anderson comes before Zurinsky. If it's just the opposite, Zurinsky is, here's Zurinsky and then here's Anderson, it would return something positive, in which case we know we don't need to look at the first name. So what I'm going to do is I'm going to store that into a variable. Int result is equal to this. If it's 0, then what could I do? Well, if it's not 0, if result is not equal to 0, that means it's well ordered, that Anderson comes before Zurinsky, Zurinsky comes after Anderson, so I can return result. I don't need to look at their first names. Otherwise, and I'll just write else if to drive home the point here, result is equal to 0, then I need to, we've got a tie, right? Same last name. So if they've got the same last name, what should I do now? I should look at their first name, right? They're both Smiths, and so Adam Smith comes before, I think I said Balthazar Smith, right? It's best to choose uncommon names so that you don't single anybody out, right? So let me go ahead and do it again. Int, or result, is equal to strcmp, but now we'll compare their first names. First name and Y's first name. Okay? Now I'll return result. Now what if we happen to have two, Adrian Smiths? Adrian Smith, Adrian Smith. What do we do now? Or Smith, comma, Adrian, I should say. Smith, comma, Adrian. What do we do? Maybe it's fine that they're equal, right? That it's okay that they have the same last name, same first name. If we wanted to break ties, well, we could break ties then by GPA, or go to their NUID and break ties that way, or something like that, right? And then we would reuse some of those other comparators. But ties are fine. So return strcmp. There may still be a tie, but that's okay. Now, if it's not okay, if you have an application in which you need to distinguish between two structures or two objects absolutely, then you need to, as a tiebreaker at the end, you need to come up with something that's unique. In this case, what uniquely identifies a student would be their NUID. You can have two John Does with different, but presumably they'll have different NUIDs. That would be the tiebreaker for that. If you're sorting bank accounts and they have the same balances, they have the same owners, then you would go probably with something that's uniquely identifying, like an account number. Right? This is why it's always good to have, when you've got data, that you have a distinguishing, a unique way of identifying that data. You'll see an example when you do hack 14, the last hack 14, and your final assignment. What we have you do is some data crunching with some transactions. And every transaction, the data set that I originally got did not have unique identifiers. I wanted unique identifiers, and so what I did is I modified the data and had a UUID, a universally unique identifier. It is a 128-bit number that is somewhat randomly generated, and then it's thrown through this hash function. What does one look like? Here's one. Here's something that looks like it. Even if you randomly generate these things second after second, with very, very low probability, are you ever going to have two UUIDs that are the same? I could have a server on one side of the world and another server on this side of the world, have them exactly the same moment generate a random UUID, and the odds that they would be the same are 1 to several hundred billion, several trillion to 1. Right? The odds are astronomically low. In fact, do they have the odds here? Find odds. Nope. Probability. Well, probability is not 0. It's close enough to 0 to be negligible. Okay, they don't have an exact number there. Probability. Okay, there it is. 2.71 times 10 to the 18. So extremely small probability. If you do end up with a UUID that's the same through the actual generation process, you just wasted all of your luck. You should have bought a lottery ticket instead, right? Because winning the lottery is more likely than this thing right here, right? All right. With only one ticket, I should say. Right? So that's how you search, or that's how you sort in practice. What about searching in practice? Well, I'm not even going to bother looking at like a linear search. Instead, I'm going to jump immediately to binary search because that's the one that you're probably going to want to use. You will get exposure to the linear search algorithm that's provided by the standard library in lab tomorrow. But here's B search. What do you think B search stands for? Binary search. Why they didn't write it all out, I don't know. Again, they're saving bytes 40, 50 years ago. It's actually not in the standard library. It's in a library called search.h. The linear search one, lfind and I think search L or something like that, lsearch. I think that they're both in the standard library, but for some reason the binary search, I guess, no, what I'm saying is, sorry, the linear ones are in search.h. The one that I want to look at is in the standard library, B search. Looks very, very familiar. It takes 5 inputs. Ignore that first one for a second. What about those 4 inputs? Base, nel, size, and compare. What are those? Exactly the same. Exactly the same as QSort. Remember that binary search, for it to work, it needs to be sorted. So if you quick sort it, QSort it, using those 4 inputs, and then you want to do a binary search on the same, in the same manner, then you would use the exact same 4 arguments, right? The only difference is the first argument. The first argument is a key. And it's also a const void star because it needs to be generic. It needs to be a pointer to it so that B search can hand it off to a comparator and say, when it's looking through the array, it says, is this equal? No. Oh, okay, well, I know that it lies in this half or in this half because the comparator told me so. The comparator returned either 0, oh, you found what you're looking for, or the comparator returns something negative, in which case it's going to it's going to look at the left half of the list, or the comparator returns something positive, in which case it looks at the right half of the list. Right? So let's actually go ahead and use this in our example. Again, we're going to have to restrict ourselves to the arrays here. Let me go ahead and get rid of that. Let me go ahead and try to find, I don't know, let's try to find 8. So B search. The last 4 are exactly the same. Okay? But the first one is a key element. Right? Now I need to create this key element. I need an integer, right? Int key, or k, is equal to 8. I'm going to be searching for 8. This doesn't make a whole lot of sense searching through an array of integers, because if you've already got the integer 8, why do you need to go searching for another 8, right? But it makes a whole lot of sense when you're searching for a student. I've got a student with NUID 1, 2, 3, 4. I don't know what the rest of their stuff is, but search for through an array of students for one whose NUID matches 1, 2, 3, 4 using the NUID comparator. Oh, okay, here you go. Oh, okay, their first name, last name, and their GPA. Now I can find that, right? They're called basically key structures. So I guess I could have passed in key there. Does this match? It needs a const void star. If I put in k, is that a const void star? No. So what do I do instead? How do I make that into a star? How do I make it into a pointer? I use ampersand. Now, right now, technically, it is an int star by doing this. But that's OK, because when I hand it off, that's when it becomes a const void star. It's basically becoming something more generic. It's specific at first. It's an integer star. It's an integer pointer. And then when I pass it in, it becomes more generic. It loses its specificity. Okay? And of course, what does it return? It returns a void pointer. That is a pointer to where it found it. What do you think it returns if it didn't find it? Null, right? Int star ptr, I'll say, is equal to this. And I'll go ahead and do the typecast myself here. And then I'll go ahead and printf %d found at memory location %p to print out a pointer which contains %d and the line. So what I'm going to print out here is the original key, the pointer address, which is ptr, and then I'll dereference the pointer address to get the thing that's actually located at that memory address. Let's go ahead and run this. Oh, darn it. What's wrong? Oops. We need to go all the way back up here. 53. What's wrong? Const student star. Passing argument 1 of CMP int. What? Oh, darn it. Okay, we need to change those into pointers. Oh, no, what am I doing? Okay. We need to change these into pointers. Sorry. Because the other comparator expects them to be pointers. So to make them into pointers, I use the ampersand here. And I don't remember the order. Does arrow come first? I think it does, so that these parentheses are not necessary. I'm being extra careful here, though, by doing this to make sure that the point that happens, and then that happens, and I think we're good now. Try it again. Oh, missing in parenthesis where? Right there. Okay. And now one more on 66. Strcmp, what's wrong? And plus, oh, okay. What do I need? If I'm going to do string stuff, I need the string library. Fine. There we go. And then 90 for, what did oh, and I missed my semicolon there. There we go. 8 was found at memory location, blah, 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 blah. Who cares? Which contains 8. A successful search. What would an unsuccessful search look like? I don't know. 42 is not in there. Right? Let's see what happens now. exit status 1. Why? What am I doing to, PTR will be null, so what am I doing to a null pointer here? Remember what Bret Hart said, do not dereference a null pointer, right? So I would have to put in an if statement here. If PTR is not equal to null, then successful search, right? Else, printf, not found. There we go. There we go. And let's run this again. Not found. You didn't find 42 because 42 was not in there. Let me go ahead and change this back to 8 and verify that it still works. Great. What if I change something? I'm going to change the comparator. Let's find out if this still works. Not found anymore. Well, wait a second. 8 is definitely in that array. Why didn't it find it? What did I change? I changed the comparator. How did I sort it? I sorted it in descending order. How did I search it? I searched it in ascending order. So what's going to happen here? Binary search is going to go to the middle and assume that since we're in ascending order, oh, 8 is larger than 6, so where should I go? That way. When it should have gone that way. So the takeaway from that is if you are going to do a binary search, again, it has to be on a sorted array. Not only does it have to be sorted, but it has to be sorted in exactly the same order as you search it. If you use 2 different comparators here, then you're not going to get the results that you're looking for. Let me go ahead and go back to it, see that it still works. All right, now it works. What if I did something completely wacky? Double. Not found. Now what am I doing? I'm surprised I didn't get a segmentation fault out of this, honestly. Actually, no. I'm not surprised because integers are smaller than doubles. So it's definitely not doing what we want, though, right? If you are going to use a comparator, well, I'm using a double comparator for an array of integers. Those types do not match. There's no compiler error. There's not even a compiler warning. I wonder what would happen if you ran this through Valgrind or something like that. It would probably catch it because it would say, wait a second, there's a type incompatibility here. But I would have to test that with Valgrind or some other tool out there. But you not only do you have to have the same order, you have to have the same comparator. Whatever comparator you're using has to be the same type that you're sorting or the same type that you're searching. You can't expect to use a comparator for students for an array of integers or vice versa. A comparator for integers for an array of students, that's not going to work. Right? They have to be the same types. You have to be consistent about your 4 arguments here. And again, those 4 arguments are going to be the array itself, which it's going to make changes to, the number of elements in the array, so the size of the array, the size of each element, the number of bytes each element takes, and then finally the comparator that you're using. And to pass in a comparator, remember, it's just the function name. That's all. Right? You're not going to have many opportunities where you're actually going to be creating your own function pointers. You're just going to use them. You want to do quicksort, you want to do B search, you want to do lfind or lsearch. You just need to pass in the name of the function. When you pass in the name of the function, you do not put the parentheses there. That invokes a function, that calls a function. The function without those parentheses, the function name, that's its reference. That's its function pointer. Okay? Any questions? No? All right. As a preview here, so again, this week we'll finish out searching and sorting. We will have Monday lecture, but of course it's recorded. No Tuesday lab. Then after the break, 2 weeks when we come back, we'll be covering stuff that's not directly on your assignments, but graphical user interfaces and database systems. Database systems kind of provides a dovetail into the next course in which you will be doing heavy database stuff.